Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video we're going to start our presentation of binary heaps. So heaps in general are an alternate data structure that we can use for implementing a priority queue. And you should recall that a priority queue has the same methods as a regular queue in that you can add things and you can remove things, but when you remove them you get them in the highest priority order. We previously implemented our priority queue using a sorted linked list, and that had the advantage that when we pull things off, it's an order one operation because we can just take off the front of the list. However, adding was an order in operation, and so building an entire priority queue that way was order n squared. And as you probably learned by this point, order n squared winds up being problematic once n gets large. So we want something that's better, and heaps, it turns out, give us order log n performance for both adding and removing, so that the operation of building a very large heap winds up just being order n log n, which scales much better for large n values. So we kind of want to understand what a priority queue, or what our heap is, and what we can do with them. So first off, the heaps are generally represented as trees. And our binary heap, as you can tell from the name, is basically going to be a binary tree. Whereas when we looked at binary trees previously, our binary search tree had the rule that things that were less went to the left and things that were greater went to the right. Our heap, viewing our heap as a tree, is going to have, we're going to follow two basic rules. One is that it has to have heap order. And what that means is that the parent is higher priority than children. Okay. Note, it does not matter whether the left child or the right child is a higher priority. All that matters is the parent is higher priority than its children. So that's our requirement for heap ordering, which is a fundamentally different ordering than our BST, but it's all that we need for building a heap and doing the operations that we want for a priority queue. The second operation, or the second requirement that we have for our binary heap, is that the tree is complete. Okay? And this one is very significant. The idea that the tree is complete means that we're going to fill in each level from left to right one at a time, and we don't allow any gaps. Now, this is very significant because this is the reason why we can guarantee that our operations are log n. Okay. Remember, in our binary search tree, it was possible the tree could become unbalanced and that you could have one branch much longer than another, and the binary search tree could degrade to being order n. It could basically be a very slow linked list. Our heap will not be able to do that. Our heap, because of the guarantee that it is complete, that we fill in each level from left to right, every element, that sets up for the fact that the height of the tree has to scale as the log of the number of the elements, and for that reason we are guaranteed, as long as all we do is go from the root down or go from a leaf up and we don't do a whole bunch of traversing through the tree, we're guaranteed to have order log n performance. And so what we're going to do in the next video is we're going to talk about how these two rules come together in looking at this as a tree, and then we'll see that when we write these, we're never actually going to write them as a tree. So we'll come back and look at